Yeah, so very informal. Mostly here to answer your questions. We can go over some homework solutions if you guys would like to do that. We can go back and review some of the lecture notes if you guys would like to do that. You know, I'm curious what you think you need the most help with. Anybody have a suggestion, or you want me to start going over some homework solutions?
I would like to do a shear flow example if possible.
A shear flow example? You mean other than the homework? Or
you can just work through one of them.
Okay, unfortunately, I have to remember which homework we covered shear flow in. Maybe without 6 or 7?
Let me go grab my stuff.
All right, I'm looking at homework 7 at the moment. Not seeing shear flow there. Oh yeah, okay, homework 8 is really where it's going to come. All right, you guys there? I forget who asked the question. Was it you, Jeremy, or maybe Scott? I'm not sure, but
no, it was me.
Yeah, okay. So you want to do the, you know, we could, I think a good way to do the shear flow examples or to talk about shear flow is actually in the context of doing shear center, because you kind of kill 2 birds with 1 stone. You got to do shear flow to do shear center. And so if you don't mind, maybe I'll start there.
Yeah, that's fine.
All right, I'm sharing now. This is the solutions for homework 8. The problem was to locate the shear center of this thin-walled section. You know, the coordinate system was given. A few exam hints going forward. I would say typically I'm going to provide a coordinate system for you. That's just a practical matter for me, because if I allow you guys to choose your own coordinate system, then it makes grading infinitely harder, because I might have 5 or 10 different coordinate systems that would be present in the solutions. And so trying to interpret your work in different coordinate systems, it's just time consuming. So typically when I write an exam like this, I actually give a required coordinate system, a reference frame that you guys need to use, so then your solutions come in consistent with that one frame. So anyway, the question here is locate the shear center of the thin-walled section. Assume a wall thickness of T, and T is much smaller than the radius. This is pretty conventional setup for a shear flow problem. Open cell, obviously, we don't have a closed cell. We're asked to find the shear center, which implies that this is essentially a bending problem in some sense. Now, you know, again, the first thing that you always want to do is classify the problem, figure out what approach is going to be the best engineering approach to solve the problem. So because we're asked to calculate shear flow, we know shear flow is a property, or I should say the shear center. The shear center is a property of the cross-section, just like the area moment of inertia is property of the cross-section. The cross-sectional area, for that matter, is a property of the cross-section. So these terms are all really relevant to bending problems, although in this case you're not actually calculating beam bending, you're just calculating, much like you would the area moment of inertia, the shear center location. But to do that, you need to assume that a resultant shear stress is present on the cross-section. That's a bending resultant shear stress in order to do the calculation. Okay, you guys all with me on that? I know there's not that many, so you guys just go ahead and turn your mics on and give me some feedback. I'm not seeing you guys while I'm talking through the solution, so please go ahead and give me some verbal feedback as we're going. Okay, so anyway, to find this, we need to, for any particular shear flow or shear resultant, we need to calculate the shear flow. Some hints on how to do these problems. Let me go back to my blackboard here for a second. Let me. It's going to take me just a second. Let me share the. I'm going to share my whole screen instead of just the one thing here. So here's my entire screen. Okay. Close some stuff out here. Okay, so here's the problem. We need to, the first step in this problem is to assume a shear resultant. Okay, and so we need to have some guidance for what some good shear resultants are. A good shear resultant, so if this cross-section happens to look kind of like this, and it has a symmetry to it, right? So anytime you have a symmetry, when you're doing this type of problem, first kind of draw it on there for yourself, and then you want to assume a shear resultant that is not parallel to this line of symmetry. You in fact want it to be perpendicular to the line of symmetry. So in this case, it's going to either be up or it's going to be down. I always tend to put my assumed resultants off the cross section, just because when you're drawing arrows in the cross section, it gets a little messy. As you move it off the cross section, it tends to be clearer what your reference lengths are and distances. And of course, here was our defined coordinate system. So we're going to start with this assumption. Now, I don't remember in my solution where I put it, whether I put it on the left-hand side or on the right-hand side, up or down. Either one doesn't matter. Okay, but so we're going to get to that point in a minute. Let me jump past the moment of inertia calculation. That's something that I think you guys can probably do, or we can go over that also if you want to. But for the moment, we don't need to do that. I want to get to the shear flow calculation. Okay, so here's the, let me see how to annotate PDFs also. So this is the calculation of interest here. So for our symmetric cross section, of course, because of symmetry, the value of IXY goes to 0. And we're going to assume, as I drew, a shear resultant in the y direction. So then the rest of this integral that had Sx in it also goes to 0. So the shear flow calculation greatly simplifies and just kind of looks like this. Now, by the way, in this homework solution, I started by obtaining the value of the moment of inertia. I would not recommend that on the exam, though. What I would recommend on the exam is you assume things until you need to know them. So you don't really need to know Ix, Iy, or Ixy right off the bat. You probably will need to know them eventually, but you don't know that you're going to need to know them. And so to save time, don't calculate them unless it's discerned later in the problem that you actually need them for something. So I'm going to go ahead and skip that part for now and go ahead and get straight to this part. Now, this is an integral. We've got a boundary condition, Q0. This is at the start. Remember, that boundary condition by definition is at the start of the S coordinate system. So Q0 at S0. Okay, and we're integrating over the domain 0 to S of this function T of S, Y of S, ds. Then we multiply that by the ratio of Sy over Ixx. Keep in mind, Sy and Ixx are constants for the cross-section, so really the only challenge here is doing this integral. Okay, so we can go up and look at our problem. Here I see that the wall thickness by assumption is going to be constant. So t actually can come outside of the integral. The next thing we need is y. Okay, we need y relative to the centroidal location. Anybody have insights as to where the centroidal location is going to be?
Of the entire structure to the left, but centered.
Centered in which, what do you mean centered?
On the x-axis towards the left.
On the x-axis towards the left. So you're saying it's going to end up being somewhere in this region right here where my mouse is.
Correct.
Okay, so that's actually quite a reasonable statement. Remember, we have this line of symmetry, and we need the y value relative to the centroid. So you kind of already said the magic word. It has to be on the x-axis. Okay, so consequently, we know it's going to be here. We could make an assumption about its location. We actually don't really need to for this problem, because all we need to know is that it's going to be some distance away from the y-axis. So this is our measured y. Okay, now we need to be able to discern y for all of these locations relative to this location as we move along this integral, around this. It's not a circumference because it's not a circle. It's not complete, but as you move from, we're starting perhaps S here and moving around this direction. So we need to know what S is here. We need to know what S is as a function of X and Y as we move around all the way down to here. So turns out for a problem like this one, the way it's drawn, I've given you some hints in the sketch. Okay, there is this upper portion of the structure is semicircular. So it's a half circle connected to a vertical web section connected to another half circle. So if you look at every place along this line, or I should say this semicircle, we can define the y location relative to an r theta coordinate system. Really only theta matters, where we now going to define theta with respect to this center point and start, say, theta is equal to 0 here at this edge, and then it works its way around to pi over on this edge. And then, of course, the distance from center to center of these semicircles is 2r. So whatever the y distance of that angle is, plus r is the y distance of that location. So we're going to exercise this change of variables. It's a pretty simple process, really. Okay, so here I wrote that y as a function of theta. It's going to be equal to r sine of theta plus r. So here, again, let me go back to my sheet here. So now I'm just looking at the semicircle. Here's my center of that semicircle. I've got some angle theta here. So this height is just r sine of theta. And then you add to that the value down to the symmetry line, which is r. So pretty simple. R sine of theta, where'd it go? Y. Yeah, so r sine of theta plus r. And so since t is constant, we can plug y of theta into there. Now instead we have to recognize we're doing a change of variables. We're not going from 0 to s. We're going from theta to theta. And so after we do that change of variables, this change of variables is actually fairly important, right? So what we have is an initial location. So an arc length location, so S would be equal to the radius times theta, right? Measured from here in this change of variables. For example, if we went, what's S all the way around at the other side? That's pi in theta terms. That arc length is pi times r. Of course, we know the total circumference of a circle is 2 pi r. and half of that is pi r, and so that gives us kind of this strong hint that, you know, this arc length is equal to r times theta, and so this is how we're doing our change of variables. And so what we then do in this integral, where'd it go? Here, in fact, here I detail that change of variables. So ds becomes r d theta. The integral now goes from 0 to pi. So I did that change of variables and showed it explicitly up here when we calculated the moment of inertia. I didn't, and so I just carried that forward down here. But that's what we did, a change of variables. So for that portion, for the portion of the structure that's kind of this region up here, we're going in an r theta system. Then once we get to this point, now we're going to start with a new coordinate system that's just a Cartesian system that has, you know, straight x, y coordinates going up and down. And then once we get to the bottom, we're going to do another change of variables and go into another r theta coordinate system. Okay, so anyway, going through that process, then just applying and calculating the integrals, applying the boundary conditions, we can calculate that the value of the shear flow Q as a function of theta is going to be this. And herein you've seen that I've done that change of variables. So from 0 to s becomes 0 to theta. We multiplied by r, pulled the r outside because it was a constant. So that's what that was. Then we plug in y as a function of theta. Then we integrate in that new coordinate system. And then here we have shear flow in this region as a function of theta.
Can you explain again how you go from the T of S, Y of S, ds to the Y theta, D theta?
Well, okay. So you know, I sort of just made an attempt to do that. Maybe I wasn't clear. Let me try again. So we can say that S is going to be equal to R times theta. So one of the integrals was T of S. What was the integral now? I'm drawing a blank. T of S.
T of S, Y of S, yeah.
Yeah, Y, thank you. Y of S ds. Okay, and then we said y was equal to r sine of theta plus r. We can take dy and we can say that, well, how do I want to do this? So the integrals with respect to s, so I'm going to go ahead and differentiate here s first. So ds is equal to r, which is a constant d theta. So I plug that into here, and now we have t y of s, really y of theta, times r d theta. Then r is a constant, so that gets pulled out of the integral. Here is my equation for y. I plug that in here, and t is a constant, which also gets pulled out. So t and r come outside. Y goes inside in this substitution, because here it's written as a function of theta. And the ds gets substituted for a d theta with that. Nicole, did that make sense? This is much easier. This is much easier on a chalkboard because my handwriting is bad enough on a chalkboard. It's just absolutely terrible with a mouse clicking on a desktop. But
That's okay. So is the y of s equal to y of theta? Like that's kind of what it looks like comparing the two integrals.
yeah, so when we wrote the initial integral, y is a function of s written in terms of ds. You know, s doesn't show up anywhere in this equation except implicitly in theta. Okay, you could actually do a substitution here if you wanted to, and you could solve this theta is equal to s over r, and then you could plug that in, and then you could plug that in here, and now you have y written as a function of s. But there's really no sense in doing that, because as soon as you make this change of variables, it needs to be a function. This integral of t y of s, or it's t times y times ds, right? So either of these are functions of this. Now you don't actually have to put the functional notation here. You don't have to put an s, y with parentheses s. You could leave that functional notation as it is, just t and y, and implicitly in that, those are functions of s. And then you can do your change of variables like I did, and you end up with t comes out as a constant, r comes out as a constant, integral y d theta. That's that substitution that I did. And this is still just implicit. And now if it happens that your y is written in terms of theta, you're in great shape already, which is kind of what I did. Does that make sense?
Okay, so just basically make sure the y is written in terms of theta, because that's because of the d theta.
Yeah, it needs to be written in terms of the variable that you're integrating with respect to.
Okay.
Okay, so anyway, once we made that series of substitutions, now it's just integrating, you're integrating y ds where y is, or I'm sorry, you're integrating y d theta where y is r sine of theta plus r. And of course, we pulled an r outside of that. So now we're just integrating, 1 plus sine of theta. And it turns out that once you do this integral, this is the result you get. Well, let me step back one. This is the result you get. Okay, this one here. But then subsequently, if you do have Ix calculated, then I made that substitution to bring it here. Okay, unfortunately, these PDFs are not as easy to annotate and so forth, but I'm doing my best here. You see what I just did? I know that was, so I integrated this equation after pulling an r out. So then what was left in here was just sine of theta plus 1. And then I integrated that with respect to theta, and I got a cosine of theta minus 1, and boom, there we go. And then, but in this case, the Ixx would be unknown. On an exam, you might calculate it at that point, or maybe you might even continue to defer that calculation till later because you don't really need it. Okay, so either one of these now expresses the shear flow. So go back to my, where are you guys at? So Jeremy, that gives you a bit of a beginning of a calculation of shear flow. We can certainly continue down that path, but with respect to calculating the shear center, something that I think is useful in this particular example, it's one of the reasons why I like to give this type of problem on a homework, is that unlike most of the stuff we did in lecture, when we're calculating the shear center, let me go back to my board here. You guys, in lecture, we did this. We did all sorts of problems where we had straight sections, and we calculated the shear flow up here and the shear flow down here and the shear flow down here. Now we've got a curved section. Okay, when we were doing these in lecture, we replaced the shear flow times the distance with a shear force, and we might have called that F1. And here was another one, and we called that F2. And then here was another one that we called that F3. Okay, and those are sort of sub-resultants of the whole resultant, where the whole resultant was out here. Okay, and then we eventually said F1 plus F2 plus F3 needs to be equal to this. And our moments needed to be equal to, whatever was appropriate. Moments about the shear center would have to be equal to 0. Moments about any other point would mean that this moment resultant was equal to the sum of those moment resultants. Now, what's happening in this problem is a little bit more creative and complicated. So this is a harder problem for sure. Why is it a harder problem? Because at each differential ds, so each differential length, has a shear flow, which we know to be equal to dF, right? It is a differential force on a per unit length basis. We call it shear flow. Now, whereas in the other examples that we did in class, we could use the fact that this was straight to replace this with a resultant F1. This was straight to resultant F2. This was straight resultant F3. We don't really have the ability to sum the forces quite as easily in this problem here. All we can do is have the differential forces and the differential and the direction of that differential force. So when we're summing the forces in X, F1 and F3 are obviously in the X direction, F2 is not, so we neglect F2 there. We sum F1 and F3. Here in this aspect, we can only count a component of that total dF magnitude in the, it has components in both the X and Y direction. So in some ways, we almost have to skip the sum of the forces and instead jump straight to the sum of the moments, because here in this portion, we can actually compute a moment contribution about the center point, where now dm, let me see if I can make some more space here. I don't think we need this example quite as much. Okay, so we can write dm, a differential moment. Well, what's a differential moment? That is a differential force times a radius or moment arm. So that's going to be equal to dF times the radius, in this case r, which we know, of course, dF is q. So q times r now becomes the differential moment. And when we sum the moments, what we're really doing is we're integrating the moments now from 0 to theta. And so when we do our global equilibrium, we're doing a moment equilibrium, sort of as our primary thought process. And then when we do the force equilibrium, when we're summing the forces in the X direction, I'm going to go ahead and delete everything. So to sum the forces in the X direction, well, we have to think about that carefully, right? So here at this location, we have a differential force that's in this direction. So at some position theta, the direction of that force has components. So it's actually only going to be, so the X component of that force is going to be equal to sine of theta times dF, right? And let me go ahead and start with some brain exercise here. So, if this is, theta can start at 0. So the component of force from the differential force, which at that point is vertical, the component of force has to be equal to 0. So let's sanity check what I wrote down. Sine of theta. So sine of 0 is 0. So there is no vertical component of force when theta is equal to 0. Okay. So here at this next location, so theta is equal to pi over 2. So the component of force is actually in the negative direction. This is the differential force here. So the force contribution, the sum of the forces in X, is actually the integral of minus sine of theta dF, where dF, of course, now is going to be equal to q times r d theta. Does that make sense? Let me hop back to your faces.
Yeah, it's just hard to get. Just initially.
You mean, what do you mean it's hard to get? So what you're saying, it sounds like, is, you're given this problem on an exam. You don't think through to that level instantly. It takes a little bit of time for you to realize that it's only a component of force. Is that what you're saying?
Yeah.
Yeah. I mean, that I agree with you completely. I think that is an experience thing. You gain that. You gain that through practice, right? The instant recognition of that aspect of this problem comes after having done it 2 or 3 times. So, practice makes perfect. I always like to say you're not going to be a professional baseball player the first day you go out and play baseball. You're not going to be a professional test taker the first time you do a practice problem. So you gotta work at it, and when you go through and you do 3-4 examples, you'll be a ton better than the first one you look at. So I agree with you completely, Jeremy.
All right, thanks.
Okay, so anyway, for this particular problem that we're looking at, so we're gonna calculate the shear flows in this first section. Calculating the shear flows in the second section actually super easy, just like lecture, just like the homework. You guys have seen that so many times now. And then calculating the shear flow in the third section is very similar to calculating the shear flow in this first section up here. So, and then of course, when you do the sum of the forces to ensure global equilibrium, like I said there, we got to do this change of variables from r to theta. Compute your sum of the forces is actually an integral rather than a discrete sum. You do 2 discrete integrals, top side, bottom side, and then of course there's no component of x in this vertical one, and it's entirely component of y when we're doing the sum of the forces of y. Anyway, thinking through all of that, it's not terribly hard once you get the big picture of how to do it. And then the sum of the moments is similar. I kind of already wrote down the sum of the moment integral equation. So that begs another interesting point is what's the ideal location to sum the moments about here? In the guidance I gave you in lecture, I said it's often best to do it I said it's often best to do it about the shear center, so you would do it about here. But now you've got this more complicated vector where the differential force associated with the shear flow there is not as easily described. The component of that force relative to the x and y direction is not easily described there. So that becomes a mathematical exercise of I need to be able to write what's this vector from here to here, and if I compute the vector from here to here, how does that contribute? And so you could do it that way, or in fact you might choose to sum your moments about some other location, right? You might choose to sum them about this point, or you might choose to sum them about this point, and so on. Or you might choose to sum them maybe in here. That's another possibility. But in all those cases, you're going to draw, components of vectors when you're doing the mathematical sum, which really in that case becomes an integral. And it's bookkeeping. It's bookkeeping, and that bookkeeping, of course, is done here in the rest of the solution that I provided. And so I'm just using vector algebra. I write the radius based on some position theta, and then I write a tangent vector, which is based on the radius, and then here is my equation for moment, and I'm tracking it in the vector sense. I'm very careful in this particular example to use vector symbolics. My ij and k direction vectors are present here, and I use cross products, and I'm very diligent about that, and you can make this work out. And lo and behold, you get to the bottom and you can do it, right? And you can do this, and then you can calculate that. And I'm not gonna dismiss this one as easy. This was not an easy problem. This was a much harder homework problem than anything we did in lecture for sure. But I gave it to you at, number one, it's good to do difficult problems because that makes the easy problems look much easier. Number two is it demonstrated that principle of integrating and doing change of variables and all those things that for any real structure you're likely to need. So, that's why I gave it in homework. And if you can understand this problem in the homework set, the exam problems are unlikely to be as difficult as that one. Now, it might end up being somewhere between the lecture examples, which are the easiest, so you can grasp the concept quickly, and the homework problems, which are the hardest, so that you actually get some real exercise doing them. They're always going to generally be somewhere in the middle.
Could you kind of explain how to calculate the moment of inertia for that problem? I get kind of confused when it's not like a simple shape, like a rectangle. Like I get confused how to do it, like for the other one.
Yeah, hold on. Hey, Buzz, come here for a second. Sorry, my son was in here. He's not used to me teaching on a Friday afternoon. Totally tangentially from our discussion today, I had some papers due yesterday for the AIAA conference. Actually, papers were due earlier this week, and the presentations were due. And so I was working on a presentation until pretty much my son's bedtime last night. And so he was so heartbroken, and he made me promise to knock off at 4 p.m. today. So we're playing the Wii Super Mario Brothers at 4 o'clock. So if you're trying to call me at 4, I'm not going to pick up. Anyway, so Nicole was asking about the moment of inertia. Yeah, we can look at that. I mean, all of these problems, I don't know if you remember back to the very first lecture, but one of the things that I said is this course can get intense mathematically, and you need to practice these change of variables, and you need to practice this, that, and the other thing from calculus. This is calculating the moment of inertia for this problem is honestly, it's just a calculus problem, right? This is not a difficult problem from a structural perspective. It's conceptually easy structurally. It's just hard in the sense of, the actual calculus of it. So, really we need to do two things. We need to calculate the centroidal location, which is the integral of y dA. And then ultimately we need to calculate the moment of inertia, which you asked about, and that's the integral of y squared dA. All right, my son left the door open when he left the room, so I'm going to go close it so I don't hear them as much. Okay, so, yeah, I mean, this, again, I don't think this problem is terribly difficult if you break it down into component parts. So, of course, this is the general description of what a centroidal, this is how we calculate the centroidal location. That is when we drive this integral essentially to 0. But we need to now express this in terms of a coordinate system we can use in this problem. And again, I would highlight this idea of r theta being a good coordinate system here. And so this integral, now we need to look at what's dA. So what's dA for this portion, the semicircular portion? So dA, so this is the integral of y dA. We need to do the change of variables, and we can say that a differential area is that. So dA, we know it's going to be a constant thickness t, so we can just say, well, that we can say is equal to t times a differential arc length, which we already said was r d theta. That's what we said earlier in our discussion. So now this is dA. Okay, so we can plug that in. course, when we do that, we need to change the limits of the integral. We hadn't really specified the limits of the integral previously. You know, it was over the area. Really, this was the integral over the domain of the area. And so now I can actually just kind of write those and say, well, what's the limits? It's going to be from 0 to theta, you know, 0 to pi over, I'm sorry, 0 to pi. Got another challenge with my son here. Hold on just one second.
Dr. Gustafson, you're muted.
Thanks. Yeah, so the integral is just going to, you know, the differential area is t r d theta. Of course, the t can come outside the integral. At that point, we go back to the PDF here. So you can see I did the change of variables. So from 0 to pi, now instead of just over the area. So from 0 to pi, TR gets pulled outside because they're both constant d theta. So A was RT d theta. The constant came out. Now we just have y of theta of r. And then, of course, we know the total area. That's the arc length pi r times the thickness. And we can now integrate, you know, we can integrate this. And what we're doing is we're calculating a local centroidal area for this sub area. So what I've written here, this that I got a circle here, I don't know my keyboard shortcuts for editing PDF. This centroid is the centroid only for this section.
Professor, I don't think you're sharing your screen anymore.
Okay. Can you see it?
Yes, sir. Thank you.
Yeah, thanks for letting me know. So this centroidal location is equal to this. Okay, now remember this integral is over, this integral for the centroidal location can also be written as a discrete integral. So the sum over, so this is going to be yi ai over ai, right? So these two forms are functionally equivalent. Here now I've counted, what I've calculated is yi for this section. So now I can do that equivalently for the upside down section, the one that I'll say is down here, which is now going to have a minus sign in front of it. And then we can, of course, calculate the centroid for this location very easily. You know, that's just going to be the midline where y is equal to 0. And then so we can add the area of this plus the area of this plus the area of this. That's the total area. And we can say this magnitude times this area plus the minus of this magnitude times this area plus 0 is going to be equal to yi ai. And then in the end, after doing all that jazz, you know, it works itself out. And here we've calculated ixx. Now, you know, again, these problems are actually really easy once you kind of get the hang of it, right? I agree they're difficult the first time you see it. You're like confused. I don't get how you're going to do that. That's, oh man, all this change of variables. But, you know, we actually use kind of both forms of this integration scheme the discrete form here, and we use the integral form, right? We use them both, and it's the point of me saying that is you need to be able to go back and forth in your mind on both of those. Those are functionally equivalent. You need to see them both, hear them both, know them both, to be able to do these problems quickly, and be able to sub one in or the other depending on your particular need at that exact moment of the exam. So that one in particular is a great problem to know really well for the exam. All right, what else can I help you guys with?
I was wondering if you could go over homework 9, problem 2.
Sure. Okay. You want me to just start talking through it, or did you have a specific question?
I was having trouble doing the getting the boundary condition, like the constant on the end, like integrating that into the problem.
Okay, so which constant are you referencing now? Are you talking about the the twist at one end is just going to be equal to 0 because it's fixed end? I assume you mean something else, but I'm kind of drawing a blank on what constant you might be referring to at that point.
I'm not sure. I was just looking at my solution for it, and I was missing points on failure to integrate and apply boundary condition at 2,500 millimeters. So I didn't know if there was like an extra thing we were supposed to do, or I just missed something. Let me look back at the solution. Maybe if you just go through it, maybe I'll figure it out.
Yeah, so I suspect I suspect that now, granted, that was the grader, that wasn't me. Okay, so I'm just surmising based on the description that you just gave me, that when you integrated this equation here, d theta dz, really now note I credited Megson for this solution. So there's a textbook that I kind of stole this problem out of to give you guys. I have a copy around here somewhere of it. So it's notable that Megson's solution uses theta where we use alpha, and I probably should go rewrite this solution. In hindsight, I should go rewrite this solution and write this up in terms of alpha, so d alpha dz. Anyway, so you integrate this equation, and what I suspect the grader has suggested is that you just didn't integrate the boundary condition. Where is it here? So, you're going to end up with this boundary condition here. And the reason why this is a bit challenging is because the way the coordinate system was defined in the problem, the coordinate system essentially started here at the origin and worked its way that way. So, you guys are quite used to seeing the fixed end boundary condition where, so if we're having torque around this thing here, what we call alpha, what Megson calls theta, is going to be, if we called that z is equal to 0, the boundary condition at that point would be the twist at z equals 0 is equal to 0. But the way this problem was written, or at least this solution, the origin is basically at the other end coming this way. And so the zero boundary condition, the zero twist boundary condition is actually at the location z is equal to 2500. And so, this, in your solution, I would wager that you said either you just didn't include this integration constant, or you said it was equal to 0 as opposed to solving for some other magnitude.
Yeah, that's what it was. Thank you. So
Okay.
one more question. So for this problem, if it didn't specify that the coordinate system started at the end, or is there a way to like figure that out, or on an exam would you be more specific about where it started if it required that the boundary condition was at the 2,500 end rather than the 0? Because it doesn't really give an
Yeah, so that's a good question. And the reality is, in the physical world, the real world scenario, there's no coordinate systems that are defined for you. You have to choose your own coordinate system. And I always say choose the most convenient coordinate system, and sometimes make multiple coordinate systems and make them all work together. I would say the very practical answer to your problem is, when I am writing an exam, I would do one of a couple of things. So, like the problem that we just went over, not this one, but the prior one, I need, for practice of grading, for the practical aspects of grading, to have a coordinate system defined so that your guys' solutions come in, feasibly similar. Otherwise, it's going to take me 10 times as long to grade the thing. That's one style of problem. Okay, the other style of problem is, it's an easier problem like this one. This one's a pretty easy problem. And I might set that up to make where the choice of coordinate system is yours, but then in some sense, I'm incentivizing you to create and choose the correct coordinate system to make your life easier. Because, the problem is going to be really easy if you choose the good coordinate system, but harder if you choose a poor coordinate system. But I might set it up intentionally so you might look at it and choose the harder coordinate system by default, unless you think about it. And therein, what am I testing? I'm testing whether you're really thinking through the problem before you start it, and whether you can approach these problems from a high level and see it for what it is. Oh my goodness, this would be so much easier if I did something else than what sort of I got to be careful in saying that, because I never want to trap you, and I would never set up a problem where it would be so difficult you couldn't do it if you chose the hard coordinate system. But choosing coordinate systems is part of doing a problem well, and so I sometimes actually test that aspect of it. And so the problem might take you 5 minutes if you choose the coordinate system one way, and it might take you 15 minutes if you choose the coordinate system the other way. And then in the end, half the students do it the easier way and half the students do it the harder way. And, in some cases, both sides of that fence get 100%, and because, they've both done it correctly, but one had a lot easier time than the other. So, I guess the takeaway from this, what's the lesson learned for preparing for the exam? If you look at a problem on the exam and you think that there's a much better coordinate system than what is implied by the problem, use it. Go ahead. Just define it, make it clear what you've done, tell me why you're doing it, and use it. And if it makes the problem that much simpler, great. And for that matter, if even in circumstances where I've defined the coordinate system for you, if you think there's an easier way to solve the problem in a different coordinate system, you can do it that way. You just have to circle back and translate it back to the correct coordinate system, or the required coordinate system at the end of the problem. Let me see your faces. I want to make sure that this is makes sense. Hannah, does that make sense? I mean, there are many times when you need to use 2 or 3 coordinate systems in any one problem. And just because I ask you to report it with respect to a coordinate system at the end, it doesn't mean you need to use that coordinate system throughout.
Yeah, that makes sense.
Okay, what else can I help you guys with?
I have another one if no one else has anything.
Yeah, go ahead, Jeremy.
Could you work through the last problem on the first exam? The one that only some of us got to see.
The last problem. Oh, yeah, okay. Well, so can you remind me what that problem was? Because I don't have that in a nice PDF. You know, that's in the e-learning system.
That was the one that had the technical failure.
No, I know it was the one that didn't show up for some of you, and it showed up for others because I made that quick change midstream to try and see if I could get you guys to see it. I remember believe me, I remember that incident. It was.
I can email you the email you sent us with the question.
I don't think I sent you the whole question though. I only think I sent you just the equation that was missing.
No, yeah, it says given the following strain and constitutive matrix, and then compute the normal and shear components of the traction vector.
All right, I'm going to stop sharing my screen so I can look at the email you're sending here, just because I don't want anything potentially sensitive in email to sneak through. So hold on just a second.
All right, you should have it.
Yeah, I got it. Okay. Where is we only have a few minutes, so I think I'll just describe through this rather than go through the whole solution. In fact, I don't know that I ever did the whole solution for myself because it never got around to grading that one, as you guys recall. So here's the problem here. So the traction vector, what's the traction vector? The traction vector are components of the stress tensor on a certain plane. Right? And often we're talking about an external surface because the traction vector then becomes the boundary condition. But here this is just a question of can you work through and calculate the traction vector for a given stress. Now, it does not look like I gave you stress, but in fact, I actually did. How do I know that I gave you stress? Well, because I have a strain tensor and a constitutive matrix. Now, let me see here. I can maybe just draw right on this image. Let me increase the image canvas size. All right, now let me take away the alpha channel and convert transparency. Let me see here. I'm trying to set the background white so that you guys can see it pretty well. Oops, that's not what I wanted to do. All right, I'm just gonna go back to my blackboard. That's probably easier. Okay, so here what I gave you was a strain, and I gave you a stress a constitutive matrix. So the first thing to do is recognize that in order to calculate the traction vector, you need to have the stress. So I can write the C matrix, which is 6 by 6. I could write that here, and then of course I need to multiply that by the strain tensor. Now the strain tensor can be written in vector format. So here we see the strain vector. The three normal components are all of magnitude epsilon. The shear components are 0. So this is going to be epsilon, 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 0, 0, 0. Okay, and then you multiply that by this matrix. And then that's going to give you, matrix is all given. And then so you're going to end up having components of stress. So you're going to have, x, x all the way down through, in this case, x, let's see here, what would typically be the last in the order that I like to use? xy, I guess, is the last one, actually. Okay, so after multiplying this times that, you're going to get this. Then you arrange that into a 3 by 3 matrix, and then you multiply that by the normal component that I gave you, and then that gives you 3 components, and that's it. Boom.
Cool. Easy enough. Thanks.
Yeah. So it wasn't really a hard problem, honestly. It was just a matter of, do you recognize the different forms that these matrices can, or these tensor values can be represented as? Well, let me go back to that. Compute the normal and shear component. So what I described actually just then computes n, right? The n vector, and then to calculate the components of that vector, you got to take it a step further, right? So now you've got t, right, from what I just described, and then the normal component of that is t dot n. And then the shear component of that is going to be the traction vector minus the normal component. So these 2 additional steps would also need to be in the solution. Yeah, so that one was pretty easy, right? Remember how I said I like to have an easier problem and a harder problem? That one was meant to be the easy one. That's one of the reasons why I was kind of depressed when you guys didn't see it, because that meant you guys had to just fight with the hard problem without having had an easy one to feel good about.
This isn't a question related to any of the homework sets or exams or et cetera, but I remember for homework 7, grade scope sent out an email about averages and medians and stuff like that, and that kind of information for homework 7. So I'm just kind of curious, what were the averages for homework 8 and 9?
I intentionally didn't send those out because there were a lot of people who didn't do homeworks 8 and 9.
Really? Okay.
Yeah, and that's not unusual. I would say, because the end of the semester gets pretty hectic, and you guys, I would say many students just focused on the project and basically said to heck with the homework. And then of course other classes are all kind of being in crunch time too. And then some of you who had been doing homework the whole semester and realized that you had 2 low grades that you could drop were saying to yourself, well, hey, I can drop this grade, no problem. And so just a lot of people didn't do it. So I just didn't send out those stats, but the overall grades on the two weren't great. The homework problems, I think, the one that we just went over is a harder problem, right? I think a lot of students just didn't get very far on it.
Gotcha. That makes sense. Thank you.
Yep. Just from my memory of the students who actually attempted the problem, I think the mean was on the order of 60, and I think the maximum that anybody got was probably approaching 90, 85, something like that on the most recent one. Okay, any other things that you guys would like to talk about? General questions, specific? Otherwise, we might as well wrap up, because I'm sure you guys have studying to do and other things that you're anxious to get to, as well as I.
If you had to choose 2 hyper important topics for the entire class, what 2 or 3 topics would you choose?
For the whole class, for the whole semester?
Yes.
Oh, yeah, that's a great question. I mean, I would go back through your notes and see if you can recall. I've made a point a couple of times, maybe 2 or 3 times in the semester, to say, if you remember just one thing, remember this. Do you recall me saying that?
Yes.
So I'm hopeful that when that happened, you went back and kind of circled that part of the notes. I would say there's a lot that's valuable. In terms of, I'm going to answer it in more practical terms. That means the things that you need to know for the exam. I think you need to know beam theory pretty well for the exam. The second half of the semester focuses on beam theory. So it's beam bending, beam torsion, shear flow, all of those, cellular flows, all of those are basically beam theory at various levels of complexity, right? And so that holistic topic is the topic that I probably use more than any other. More than any other structural theory, when I am trying to describe simple concepts to people in the real world, the beam analogy is exceptionally powerful for talking about structures and how structures carry load. And so that topic is really important. And so you should be able to do basic problems in beam bending, beam torsion, and the various shear flows. You should be able to, and honestly, I mean, that's kind of a cop-out answer, because that's all the homework for the last 5 weeks, right? I recognize that, but all of that stuff is equally important for your ability to communicate and think through aircraft structures going forward. Now, the elasticity theory is important, but and you use that all the time in structural mechanics, obviously, as well. But from the purposes, from the viewpoint of what's going to be tested, it's going to be the beam theory stuff that's going to be tested, more likely. Now, there might still be a conceptual question on stress and strain, or maybe a couple, but beam theory is more important. I don't know. Jeremy, you're asking which is the most valuable thing from my extremely valuable most.
You know what I'm asking. What's on the final? That's what I'm asking, but you can't just say it that way.
Well, I think I've answered that to the extent I'm willing to.
Yeah, no, I appreciate it.
Yeah. Beam theory, plus concepts. I would say that my class is the most important class in the whole curriculum, and beam theory is the most important material in my class. So there you go.
Understood.
Yeah. Some hints I'll give you. We talked about some of those. And by the way, I'm not biased in giving you these hints because I've not actually written the exam yet. I don't know what I'm going to ask you. So just some general hints. At various points along the semester, I said, in this scenario, this problem becomes easier, and then I gave you the scenario. So for example, symmetry is one of those where that makes IXY go to 0. Stuff like that. It's good to go through your notes and review all of those things, because I would say in exams, as a general rule, because you have a very limited amount of time to solve problems, it's going to be many of the times, almost always, it's going to be those, you're going to use one of those tricks to make the problems easier. So knowing those tricks like the back of your hand is pretty important. And I think I gave you those hints like 3 or 4 times through the semester. Here's a list of things. If this, then that. So go review those. All right, sounds like I've exhausted your questions.
Professor, I was trying to go through the homework and trying to find an example of beam bending, if you happen to know what any of those homeworks are. So I at least could ask you to possibly quickly go over one, but I've been trying to go through it. I don't know which one it's from. So I believe 7, maybe.
Sounds right. All right, so really you only got this one problem that's pure simple beam theory. Now I'm going to say that, but then of course recognize that is actually a more complex problem. This is honestly, it's the same problem, except it's only a second order differential equation. Both of these classes of problems are the same. They're linear differential equations. One's of second order, one's of fourth order. And if you can solve the second order one, you're great. If you can solve the fourth order one, you're even better. Okay, so the fact that there was only directly one where you're calculating beam deflections should not be considered discouraging. The other thing I'll say is a lot of beam theory requires you to do things like calculate area moments of inertia and polar moments of inertia, stuff like that. And we had other problems like this particular problem was one where calculate the area moment of inertia. This is a beam bending problem. The only reason we calculate area moments of inertia is because we're making the beam analogy. Okay, so this is a beam bending problem, even though you didn't calculate beam deflections. It was just, here's a harder problem for calculating area moment of inertia. How would you do it if this were thin walled? And that again gets to the idea that I'm going to treat it in this form rather than the integral form. I can do this discretely rather than in integral form. So anyway, all of those are beam theory problems, but I think what you were asking is, can I go over this one? So when you get a problem like this on the exam, you want to take a holistic view of it and say, well, what's he trying to get me to solve? And so, read carefully, compute the deflection and maximum stress. So your answer should have 2 parts, a deflection, maximum stress, and then you should plot the shear force and moment diagrams. Okay, so deflection maximum stress, you examine, classify the problem, it's beam bending. I know that this problem for a constant cross-section bending in only one axis, which is implied by the way the problem is set up, I can just write down the beam bending equation like this. EI times the fourth derivative is equal to the distributed load. Now you should have that equation. Jeremy, that's an equation you should memorize. You should have that equation in the back of your head. So you just write it down. Now looking at this particular problem and then applying that equation to this problem, you have a distributed load given, great, but you also have this point load given. Now the problem with a point load in thinking through that EI fourth derivative of V is equal to distributed load. This is a discontinuity in distributed load. I got to look at your faces to see if you're understanding that. Okay, you know what I mean when I say discontinuity? Alex, I'm asking you.
No, if you wanted to go over that pretty quickly. I'm sorry, I was writing out things that you were saying as you were going, so.
Yeah, no problem. Hey guys, since there's so few of you, can you just turn your screens on unless you feel like there's a particular reason why you're not? So it helps me to know whether you're still there, and I can discern whether you're understanding a little bit better if I can see your faces. Okay, so let's just introduce the idea of a discontinuity. So here's this problem, right? So it was fixed at the left edge, so that's what that looked like. And then over here at the right edge, we had this, oh shoot. Boy, I hate drawing on with a mouse. Okay, so over here we had a what we call simply supported. It's a point support, right? So that it can bend over there. So what I'm talking about now is this point force. So I'm trying to get you to understand what's the difference between a point force and a distributed force, particularly with respect to this equation, that is EI V to the fourth derivative is equal to distributed load. Okay, this point force cannot be represented easily in terms of this distributed load on the right-hand side. Now, if we had a distributed load that looked like this is a continuous distributed load. It can be described by some function, or hopefully on an exam it would be describable so that this would be something you could integrate easily. But in the limit, as this gets narrower and narrower, okay, and it ends up being very narrow, and then eventually it's just the point force, that is now discontinuity. So if you look at the, first of all, what does continuity mean? It has to do with the derivatives. So what is d by dz of the distributed load P of z in this problem? So when it was if it's continuous, that means that those derivatives, particularly the first derivatives, when we say continuity, we're talking about derivatives. So is there a step displacement or some sort of break in continuity of the derivative? So here it's a continuous derivative. As this gets narrower and narrower, the derivative goes higher and higher, and eventually you get this idea of the derivative is zero everywhere except at a single point where it's infinite, right? And that's functionally what's going on here. Now that mathematically is described as a step function in the derivative, or a Heaviside function. So we have a step derivative. So what does that mean practically for solving the problem? That means that you can't actually, because there's no continuity in the right-hand side of this equation, and you can't integrate it because you can't, you'd have to integrate a Heaviside function. Actually, in practice, you can. It just requires mathematics that we don't do very often, and it's not easily describable here. So instead, what you should do is when you have this type of problem, you just recognize, I'm going to break this up into two beams because the beam on the left-hand side is continuous and the beam on the right-hand side is continuous, and I can write boundary conditions that join the two beams together.
Okay.
Okay, so in this particular problem, the complexity of the problem comes from that aspect, is that I'm actually going to split this thing into two separate beams and then enforce continuity boundary conditions. Okay, so anyway, you can read through all of this, but the bottom line is that's what I did. So I broke it up into two beams. So here's the displacement of beam A. Here's the displacement of beam B. Okay, in this sense, for whatever reason, I used Q as my distributed load. Okay, so I integrated that 4 times. So from that, I got 4 integration constants. I integrated this one 4 times. I got 4 additional integration constants. Now I have total 8 integration constants. I need 8 boundary conditions. Okay, then we go up and look at it. Well, what are my boundary conditions? I can sort of by inspection get 4 of them. I can look at the left-hand side. This is the fixed boundary condition. This is kind of like the cantilever beam boundary condition. So the displacement is 0, the slope is 0. Okay, that's 2. I can look at the right-hand side. I can say the displacement is 0 and the moment is 0. That's 2. Now I got to come up with 4 more. Somebody's got their mic on. Could you mute, please? Thank you. So that's 4 out of 8. The other ones we're going to need to work out, but so let me go ahead and I'll go through these. So at the left edge, displacement was 0, caused C4 to be 0, slope was 0, so C3 had to be 0. Right edge, displacement was 0. Now what's interesting, again, we have this variable, this coordinate system. This gets back to Nicole. I think it was Nicole's earlier question, or maybe Amanda, one of the two of you guys, I forget which. What are your boundary conditions? So for the purpose of simplicity in this problem, I defined one boundary, or what are my coordinate systems? So I got 2 beams. Theoretically, I could have 2 coordinate systems. I could start one at the left-hand side going to the right. I could start one at the right-hand side going to the left. It's actually not the best way to do it in this problem, because then it just makes tracking the boundary conditions a little bit more difficult in my view. So I used one coordinate system and I started there. And so anyway, at the right-hand side, this is at z is equal to L. So, what does that mean? So then this equation, V, where z is equal to L is equal to 0. But now instead of having nice one clean boundary condition goes away, or one constant goes away because of this, it's not quite as clean there anymore. So I haven't actually eliminated my equations yet. I'm going to have another equation here. So now I've got 2 equations for those 4 unknowns. Okay. So anyway, I've got 1, 2, 3, 4. I still need 4 more equations. And really, there are continuity boundary conditions. Okay, now I've got to go back up here. What I'm saying is, at this point, the equation on the left-hand side and the equation at the right-hand side have to have continuity. So the displacement calculated with the left one has to be equal to the displacement calculated at the right. The slope calculated with the left has to be equal to the slope calculated at the right. There's a moment continuity here as well. So this is the second derivative of displacement. That also has to have continuity, because the moment, if we took a free body diagram here, okay, and I had a moment here and a moment here, and in the limit as dz goes to 0, if I am taking moments about the center, p cancels, and so the right-hand side and the left-hand side moments have to be equal to each other. So we've got displacement, slope, and moment boundary conditions here. That's 3 more equations. Pretty it's pretty simple when you think about it, but ends up being a lot of algebra. Okay. And then the last one, again, it's this one here. The shear comes from step discontinuity. What do I mean there? Okay, so let me go back to my blackboard. Again, I'm taking that same free body diagram. Okay, just a little differential on each side of P. So this was P. So here's V in equation B, evaluated at this position. I forget what the position was. We're going to call it Z of P. Okay, and on this face, we had V of A, again, at this location, ZP. And here, if we sum the forces in the y direction, what we're going to find is that VA, let's see here, minus VA, because that's down, plus VB minus P is equal to 0. And this gives us another continuity boundary condition. So this is the third derivative equation of the deflection. This is the third derivative equation of the deflection, and this is the point force. So this now gives us the fourth equation at this point. So slope and displacement are 0. Or I'm sorry, slope and displacement are continuous there. They're the same value. Moment is continuous there because, taking moments about this point, the P cancels. And then the shear, we've got this shear discontinuity. So this is a continuity equation that includes the point force, and it shows precisely how the shear discontinuity works out mathematically. Okay, so there you go. The shear is step discontinuous. And that's that equation. I plug in the values. That gives me this new equation. So now I've got 8 equations for 8 unknowns. And I didn't actually go through and solve those for you in longhand, because typing those equations would be awful. And in fact, I use an equation solver, much like you guys do. But anyway, 8 equations, 8 unknowns. They're my constants. Okay, then I plug it in. And oh, by the way, here now I have the actual displacement fields. Okay, and it's worth noting that P and Q, so the distributed load and the point force, can be calculated separately and summed. You can use superposition. I didn't in my own calculation, but here you can see quite clearly that you could have done that. Now, you still have to do the rest of the calculations. So, that is, so I've computed the deflection. So you need to compute the maximum stress. Well, what's the maximum stress? Well, sigma is equal to my over I. We can remember, this is a good one to remember, Jeremy. Memorize that, hint, hint, right? So from the equations that we've done, moment is the second derivative of displacement. So differentiate this 2 times and you get moment, and then you plug that, multiply by y and divide by I, and you get stress. And so that's pretty easy. And then what's the last part of this? The deflection, maximum stress, shear force, and moment diagrams. So the shear force and moment diagrams are simply, if we look at what these are the 4, another thing to, Jeremy, write these down, because these are the things that are easy to forget but very valuable. So this one was deflection, the next one was slope, the next one was moment, the next one was shear, and the last one was distributed load. So I asked you to do the shear force and moment diagram. So plot this equation and this equation. And boom, there it is. There's the moment. And here's the shear. Obviously, the shear discontinuity comes into play. It's a step change in shear. There's a moment continuity. The moment is the same at both sides, although the next derivative has discontinuity in it. So it is not, it's not third rank continuous. It's only second rank continuous, this problem. third order, really. Probably should call it order instead of rank, but so there's a discontinuity in the shear. That's the third derivative. It's continuous through two derivatives. Anyway, so that's the rest of it. And I made this note here in the homework solutions. Conceptually, you guys could probably describe this without any trouble. I mean, I would hope on the exam you would be able to describe that process. Actually doing the algebra on the exam is too much. The likelihood of making an algebraic error in that, I would say, out of the 50 plus students in the class, in the time frame you have to do the work, I'm going to say at least half of you would make an algebraic error. So that's why I don't give that type of problem with that many unknown coefficients to solve on exams, generally. In my own work in solving this, I used a symbolic solver just to make sure I didn't make any algebraic errors.
So on an exam, you would expect to do this unknown. Trying to figure out how to do it by hand, and I got kind of so like you can expect us to find the unknown by hand then.
So I didn't hear everything. It kind of came through broken, but I think you asked, would you expect me to be able to do that on an exam? Is that basically what you asked? I would not give you a problem where you'd have to do all that algebra on the exam. Now, having said that, that doesn't mean that students don't. So often if you make a mistake in setting up your problem, if the algebra gets heinous, that's probably a hint that you made a mistake in setting up the problem. I don't know how to make, I don't know what to do with that piece of information. Other than to say, if it looks like you need 5 pages of algebra to solve it, then, go back and take a peek at whether you've got a boundary condition error or something else. Now this question, because of its length in algebra, probably would not show up in that way on the exam, but you would certainly have to be able to answer conceptual questions that would be related to this. So it's actually fairly common for me to say something like, set up this problem, identifying the boundary conditions, but don't solve. If you see a problem where in the instructions it says set up but don't solve, that's likely because it's not that hard to set up, but it's a lot of algebra to solve. So when you see that problem, then you have to be very focused on getting the things right that are being asked, obviously. So you really need to think through the boundary conditions. You need to think through the governing differential equations. If that problem showed up on the exam, you would have to be able to identify that you needed 8 boundary conditions, and you'd have to be able to tell me all 8 of them. That would be an expectation for that problem if it came up like that on the exam. Okay, we've gone an hour and a half plus change with, of course, the small interruptions from my kid. I think we're going to wrap up. I do have 2 more office hours sessions before the exam, Tuesday at 11, and then last minute Thursday before the exam, Thursday at 11 also. Don't be afraid to call or email requesting some additional time. That'll just be by appointment. I'll do my best to squeeze you in. Good luck on the exam. I hope you guys do well. And I will. Thanks, Cole. And don't forget to fill out those course evaluations too, please. Maybe go out and have a nice tasty beverage before you do those so that you relax a little bit. I know this is a tough time of year for you. Okay. All right. I'll see you guys next week, and good luck.